We've already talked about how the differences between an average rate of change and an instantaneous rate of change. What we're going to do in the next part of this section is we're going to tie it into the concept of both velocity and then later on into acceleration. So just a quick recap about an average rate of change. An average rate of change of a function is basically the slope, and you used to in Algebra 1 you talk about how the points were x1, y1, x2, y2, and an average rate of change is just to find the slope between them, hence we say it's change in y over change in x. When we get into the calculus a little more, we talked about how when we did the definition of the derivative, we called this x f of x, and then we said, well, we're going to scoot it over h, and we called it x plus h, f of x plus h. But either way, when I go ahead and I, again, calculate the slope of that red line up there, in the context of the x f of x format, my y2 is f of x plus h, my y1 was f of x, and my change in x would be x plus h minus h, or just the change. And that gave us the slope of that secant line that we've been talking about, which is our average rate of change. Now the instantaneous rate of change is not what is the average, it's what's happening right here. So we need to squeeze that in, and we need to make our h, which a lot of books call delta x, I've been using them interchangeably for you. We need to make that h become basically infinitesimally small, squeezing the secant line on top of the tangent line. And it'll tell us what happens at exactly that instant. So it doesn't really matter how the graph looks like, even if I went like this. Again, if I'm on an interval and we're going to be changing it to time, and I call this my first time and this my second time, when I'm talking about the average rate of change, I'm talking about this. When I'm talking about the instantaneous rate of change, like over here, very different. It's going up very quickly right there, where the average is obviously more balanced out because it's got some up, oopsie, sorry, I didn't mean to move that, some up, some down, but we get the instantaneous from the average, which is why we tie them so closely together. So really key concept in here is that the concept that an average rate of change is technically the slope of that secant line. And we're going to be actually having it, again, over a time interval when we deal with velocity. So instead of on the bottom having x2 minus x1, we're going to have time 2 minus time 1. So you can kind of see where that's coming into play. Our instantaneous rate of change is the slope of that tangent line, or the limit process applied to the secant, and that is also known as our derivative. So when it asks you for the average rate of change, Algebra 1, slope of the line. Instantaneous rate of change, Calculus 1. What is the derivative there? So we'll start a slow tie-in to how this leads us to the concept of velocity, which there's a whole topic, what would you call it, like a category of questions on the AP exam that they call particle motion questions, where they tell you that a particle is moving horizontally, or sometimes they'll say along the x-axis. And you'll be asked different things about its movement based on time. They might ask you questions about when it changes direction, or when its acceleration is at a maximum, or what is its velocity 3 seconds in. There'll be a lot of questions, and it's a whole field called particle motion. And there's always several multiple choice questions, and every free response test I've seen in the last 10 years, there's been one of them, of the 6, devoted to particle motion. So the first concept that we want to discuss with the movement is the velocity. So what we've got is what we call a position function, and those of you who are in physics have already dealt with that. In physics, you use the variable x for position. So x of t would be where is it after time t. But our book uses an s. So we are going to have s of t. So kind of note, in our calculus context, what in physics you've been calling x for position, we'll be calling s for position. So you have to get used to interchanging those if you're taking both classes at the same time. So what I'm going to do is just give a general parabolic path here. And what I want to do is discuss this being the time axis and this being the position, or where is it after a certain amount of time. And maybe we'll want to say our time is in seconds. And maybe my position is in feet. It really doesn't matter, just to get a good concept of what's going to be going on here. So let's go ahead and take a certain time. We'll call it time 1. And we'll go up here. And actually, let's just call it t, because maybe I'll use that more formal definition. I'm going to go like that. I'm just going to call this time t, or sometimes I'll call that t sub 0, t sub 1, t sub 2, whatever. I'm just going to call it t. Then on this curve right here, I would call this point t and the position at time t, maybe as 10 feet. Then I'm going to scoot over a little bit here. I'm actually going to scoot over what we would call delta t, or change in time, and I'm going to have another time value right here. And again, I'm going to go up on my graph. I'm going to say, well, okay, here's my next time. And in terms of our calculus, we'd call this t plus change in time, and we'd call it the position at the new time, just so you can kind of see how that f of x plus h definition is going to tie into our position model. So if you were to draw a secant line and find its slope, what you would be doing is finding the average change in distance over time. And a lot of times you'll see this written like this: change in distance over change in time. And we know that change in distance over change in time is velocity. But if you do it as is here with this line, you will be giving me the average change in velocity. So sometimes we'll say that the average velocity, and I like to call that v sub av, would be, all right, change in position. So this is where it currently is at a change in time. Where did it used to be? And then over my change in time. This is just change in distance over change in time. That gives me an average. But again, if we apply that limit process to it and say, okay, we want to squeeze that change in time closer and closer and closer to 0, moving this dot back and back, and then when I start drawing those secant lines, what I get is what is the speed right there at time t. And that's kind of how that whole formal definition of the derivative ties into velocity. The key to it are several things. First of all, note that we call the change in position delta S, which is fine. And then we're going to talk about, well, how do we apply all this stuff? Is it really this complicated with the S of t plus delta t and all that? No. But let's go take a look at a basic, what we call a common position function for a free-falling object. The general position model, which you've been given off and on throughout the years, I think, is that we take 1/2 of gravity. You might say, well, what's gravity? Let's go fill that in first. On Earth, gravity is negative 32 feet per second, or if we're dealing in meters, it's negative 9.8 meters per second. And it's negative because it's pulling you in closer. It's like what we would call a vector in physics. It's got direction to it. It's pulling you toward the Earth, not away. So we call that a negative direction. And so really what this becomes, instead of 1/2 of g, is this will always be a constant out front. If you're dealing with feet, it'll be a negative 16, half of the negative 32 t squared. I'll write it like that. If we're working in a problem in the metric units, then that would be, what would it be, negative 4.9 t squared, because we do half of that. So it's one of these two models, depending on whether you're working in customary feet or metric meters. And S sub 0 is what we call the starting position. All right, we just said S is the position model. S sub 0 means at time 0, that's our starting position. V sub 0 is our velocity at time 0, or our starting velocity. Now that's something to note, because when things are getting thrown, like thrown up or down or forward or etc., then we do have an initial velocity. We send it off with a force that gives it some velocity right away. But if we are simply just dropping it, then we assume that V of 0, we don't assume, we know that the velocity of time 0 is at time 0 is 0. So be careful whether they say it's something like this, where we're jumping, which does give us some initial velocity right away, or whether I'm simply just dropping something off a building, in which case the starting velocity starts from ground zero. So this is the model we're going to work with on Monday, and I'll just start it off and then we'll pick it up from here on Monday. We've got a diver jumping from a platform, and I have a picture of it on the next page in your notes. The platform is 32 feet above the water. In terms of all this, this would be my starting position. So this is why we're ending in the 32, because that's the beginning height. All right? And the position function of the diver is given by negative 16t squared, which means I'm dealing in feet per second, and plus 16t. What does this tell me right here? That tells me that my initial velocity is 16 feet per second. That's kind of right off the diving board. And we're going to be asked some questions about this on the next page. So I'm going to have you move it to the next page and then we'll stop. We're going to be talking about the diver's position. When will he hit the ground? On Monday, we're going to talk about average velocity over a time period. We're also going to talk about instantaneously, and ultimately we're going to say, okay, here's the water down here. What is his velocity right there at that instant when he hits the water? And so that's what we're going to talk about on Monday. You guys have a great weekend, and we'll see you later.